Hello, welcome to Imajo Explains. Um, I'm excited about today because I spent extra time planning. I thought I had a clear idea of what I wanted to talk about, transformations, and started writing notes. And when keeping to my 20-minute time container on script writing, loosely termed, I ended up only coming up with examples that were not exhibiting the property I wanted. So, I laid down, brainstormed, thought about it, meditated on it, worked, did tutoring. Eventually, it all coalesced, and now I have what I think is a pretty good presentation on the transformations. So, um, let's hop right in. Woo! Okay, I don't need that much of me. I can be smaller even. It's true. And this is the focus. This will come back later. Desmos, we'll graph something eventually. Okay. So, the point of this video is to have and develop an intuition for this diagram here, which the sort of way of thinking of this is initially you solve a question by coming up with the answer. There's some means by which you go from question to answer. And instead, we're going to transform the question into some other question, solve that one in a different space, and then undo the transform to get back the answer we actually want. In full words, that means, so you have a question Q, but getting directly to the answer A is hard, going straight down. So instead, you apply a transformation to get an easier question. And that's sort of the key here, that Q prime is easier question than Q was to solve. And you solve Q prime, solve it prime, to get the easier answer, A prime, and then undo the transformation with T inverse to get the answer A you actually wanted. Okay, so that's going to be the intuition, or the comparison I'm going to draw between all of these examples. And that's basically all I'm trying to talk about, is how often this shows up in mathematics, and how we can go over a few different examples in arithmetic just to get our feet wet with the concept, and then one really, really important example in algebra. So, let's talk about arithmetic. Okay, so say I buy some toilet paper in packages containing 20 rolls each, and I bought the last one 4 weeks ago, and now there's 14 rolls left. And a question I might ask in that moment is about how many should I expect will be left after another 8 weeks. And a reasonable assumption to have with that is, in order to be able to solve the problem, is let's assume that I continue to use the toilet paper at the same rate. Use toilet paper at the same rate. So if I assume that I keep using it at the same rate I've been using it, how many do I expect after another 8 weeks? Now, note that the numbers are kind of nice right now, like I deliberately picked them to be nice, and so you may jump right to an answer without really going through this whole transformation process, and that's on purpose. I want to choose examples for now where the direct question to answer is easy, so that you can see how the alternate process works. Okay, so how do we go about solving this? Well, what I'm going to convey is first we need to know how many I've been consuming. And yeah, I'll convey this first in the way you would normally see this done in a math class. So let's say you want to find the rate that I'm currently consuming. The rate of the rate of use. So that's how many. You're wondering how many toilet paper rolls in how much time. So that's going to be at 20 or not 20. Yeah, 20 minus 14 is how many I used. And 4 weeks is how long I used them in. 20 minus 14 is 6 over 4 is 4 rolls per week, which is 3 halves. 3 over 2 rolls per week. Okay. Then multiply that by the number of weeks. So how many we left after another week? So multiply that by the number of weeks to go to get how many more will be used. So you take 3 over 2 rolls per week and multiply by 8 weeks. The weeks cancel, you're left with I'll divide by 2 first to get 4 and then multiply by 3 to get 12. So that's rolls. 12 rolls. That's how many more will be used. Then subtract that from how many add, get how many we will have. I will have pronouns. This was all about me. This was a very egocentric problem. There were 14. So 14 minus 12 equals 2 rolls. And that's the answer. Now, that's sort of the straightforward way that you're taught in math class to go through it. The thing I dislike about this is it makes it feel very arbitrary, like you're just kind of throwing things around, seeing what sticks. If anything, you're letting the units follow or carry you through. But we can do better. So, let's think this through in a transformation way. So first, we're going to pretend, transform this into a space where I started with no rolls. Which may sound really weird because you're thinking, wait, what? Like, if I started with none, then how did I consume any? And we are going to use negative numbers. Okay. The use of this is going to be that if I start from a frame of 0, then it'll be easier to see what the changes are and what the final value is, and everything will sort of flow relative to the start. And that's a really common thing in math where, like, if you shift your origin, your point of perspective, to wherever you're wanting to look from, where you're wanting to start, and then look around from there, you sort of see the lay of the land more clearly. So moving 0 to be where you're trying to start is a really great idea. Sometimes you want to move 1 there, but we'll get there. So, all right. So what that means is, and I'm going to use this symbol to indicate the transform is occurring. So started with 20 rolls, needs to go to started with 0 rolls, and started with, oh wait, and then after 4 weeks, well, after 4 weeks, then have 14 rolls is going to change. So the question is, what is the transformation? In order to go from 20 down to 0, it feels like subtraction is what we're doing. We're subtracting 20. So, so we're using x maps x minus 20. So we're replacing whatever the value was before with 20 less than that. Yep. So then have 14 rolls. That means then have 14 minus 20 is minus 6. Okay, so we're now in this space where I started with none and I had minus 6 later. That's at 4 weeks, and we want to extend it to 4 plus 8 weeks. That'll be easier to read, I think, with a number, don't you think? So that's at 4 weeks, and we want to extend it to the result at 4 plus 8 weeks. Which is 12. That's 3 times as far. So let's just triple how much I used. So triple the result in the transformed space. And this is what I mean by this is way easier to solve in this transform. I started with 0, I went to minus 6. I need to go 3 times farther. It's just 3 times minus 6. So I'm going to rewrite all of this. And then say that we've got, finally have minus 18 rolls. So instead of having consumed 6, I've consumed 18. The last step is filling in that blank at the bottom left by undoing the x to x minus 20 transform. So to undo a subtraction of 20, we add a 20. And that gives us our final result that we wanted. If we add 20 to minus 18, we finally have 2 rolls, which is the same answer as before. 2 rolls. This is such a habit now of how I do this with all my students. Okay. So that's one solution. Here's this. Okay. I want the new things to be in purple. You're new. And you're new. That's not purple. That's purple. Okay. So to undo subtract 20, we add 20, and this is where finally, yeah, this is the result of 2. Okay. Now what we did in the diagram looks. So I want to keep relating this back to the diagram so that we keep having a good solid understanding of what's going on, a good visual, an intuition, a map. And the map really is, like, I tried to lay it out here as well. Like these, when we moved from the givens to this, was applying the transform. That's moving from q to q prime. Then we moved down to get this, which honestly I could probably denote. That'll probably make this better. A down arrow, out, and yeah, that looks good. That looks good. And then we undo the transform. Yeah, that looks right. And I'll just copy that. And make it purple over here. Perfect. All right. This was going from the question q to the new question q prime, solving that, getting a prime, and then transforming it back to get the answer we wanted, a. So we had this. Coming, we had 20, 14 rolls transformed into, if I type in here, is it purple? Yes, it is. To 0, -6 rolls, but it's still purple. And that was using the transform x maps to x minus 20. then we got the answer of negative 18 rolls. And then we undid the transform with the inverse, adding 20. And that got us the 2 rolls, the answer we wanted. That kind of makes sense. Wish this was space. That looks better. Yes, 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 yes. And I'm also noticing I really don't like that top area, but oh well. It's fine. Fine. Okay, so this is the first example. Now, one thing I want to mention is that frequently you can create a concept for the transform space. So this will be another note. Frequently, we can create an intuition for the what the transformed space represents. So these values in the transformed space, they weren't my actual number of rolls, they were how many rolls I had consumed. In this case, the values represent the number of rolls consumed or used so far. So that means here I could add the word used. So we converted 20 and 14 rolls, how many rolls were actually there, to 0 and -6 used. We're going to use 3 times as many, and then we convert that back. Over here, started with 0 rolls used, then have -6 rolls used. Started with 0 rolls used, 6 rolls used, finally have -18 rolls used. Started with 0 rolls used. Finally have 2. And so just adding the word used there really sort of makes it clear what's going on. We transformed into the space of focusing on relative to a 0 start, how many were being consumed, and then it was easy to find the final value, convert that back. Yeah. And then that means a little bit wasted. Okay. This is convenient and not always the case. So, yeah. All right. Having a concept, having such an intuition is convenient, but not always available. It is not always available. So like, there are times in math where there ends up being a really nice abstract space to work in, and it just doesn't represent anything physical. You're literally just removing components, abstracting away, and transforming into just something completely different just to make the math easy. All right. I think I'm almost at time. I kind of want to present the others though. yeah, I'll present the others and think about them, and then I'll solve them later. So, let's consider a geometric sequence. To be clear, this is not a geometric problem. It is still an arithmetic problem, but we're going to be solving one that has a geometric sequence where the last one was an arithmetic sequence. And to be clear, these don't have to be sequences. This could have been like, rather than being exactly three times as much, 3 times as many weeks, if it was, 10 weeks and you had to figure out, multiply by 10/4 to get this. I hope it's clear how much easier it would be to think through it in this way than to try to go directly from here to here, going from this 4-week change to what the result will be in 10 weeks. It's a little harder to see what's going on here. It's really easy to see what's going on here. That's the intention. Okay, so I put 600 in a savings account, and after 3 years, the account had 2,000. The question that I might wonder is how much should I expect to have in the account after another 6 years? And I am deliberately choosing something that, again, is twice this. The numbers are pretty, so that it's just 3 times the amount of time from the start. And again, you can do this in a straightforward, direct way because the numbers are nice. And I'll show that, as well as a transformed way where you transform to the perspective of, from the perspective of the start and how much things are changing. And then in that change space, solve the problem really directly, really quickly and easily, no matter what this number would have been. And then convert that back. So yeah, I challenge you to try to think of those 2 ways of solving the problem, what those might look like, and in particular in the transform space, what the analogs to all these parts would be. I'm gonna just copy this over because that's gonna be handy. Yeah, all of this is handy. Okay, and then as an aside, next time I'll mention how log tables or using a slide rule as a log table is a way of calculating difficult multiplications by hand very precisely, using addition instead of multiplication. And if you don't know anything about that, don't worry about it. I'll explain it then. But it's a nice aside about how we've used this in arithmetic. This was something really important to know how to do before the advent of the mechanical calculator or electronic calculator. Before we had calculators, this was what human calculators would use a lot. And then the last thing that we'll cover next time will be, hopefully, if I have time, well, the culmination of our efforts is to apply this to a much more difficult case of solving a quadratic equation. In this case, this one here. And we'll try to do it in a sort of 3 blue, 1 brown style where hopefully by the end you understand how you could have figured it out on your own. If that's the case, if you do feel that way by the end, then you'll have understood this method enough to apply it to new kinds of problems. But yeah, basically, this is a polynomial that trying to solve for its zeros isn't straightforward. It's not factorable, and plugging in test values will show you around where the roots should be, but it won't the roots are not, they're irrational. So they're not something you can just grab with your hands right out the gate. And so you clearly need some more powerful method. And that's where things like completing the square and quadratic formula tend to come in normal rote schoolwork. We're going to do a method that is more intuitive, actually equivalent to these methods. I mean, completing the square is actually technically kind of equivalent to applying the quadratic formula, but anyway, we'll end up doing something in a transformative way that I hope will make everything else more intuitive. So you get to look forward to that. And that's the plan. Hopefully the intuition for this process is being made more clear and feels more familiar. And sorry we didn't get to the highly anticipated, I'm sure, Desmos grafting part of this process, but that's when we get to the algebra. We're going to need to graph that quadratic to see what the transformation space actually meant. I wonder if this will lead into me talking about projective space. This might end up with me ranting about projective geometry, which I love. So maybe we'll get there. See you next time.